Okay, so let's go ahead and get started. So the first thing that we'll do today is go over the homework. So I need to remember exactly what that is. So in the homework I tell you that you have some electric field. E vector is going to be equal to E0 times x hat. Okay, so this is just some constant electric field in all of space that's going to be pointing in the positive x direction. So if we wanted to draw what this looks like, that would be like this. So the first thing that we wanted to do was to find what the electric potential function is, and for some reason I capitalized function here. So in order to do that, what we say is that V is equal to the integral of E dot dl. And then we can identify dl here to be the dl for Cartesian coordinates, because this electric field is written with an x hat, not an r hat or a theta hat. And so this dl is just going to be equal to x hat dx plus y hat dy. And so we can plug this in and evaluate. And so what we see is this is the integral of E0 x hat dot x hat dx plus y hat dy. And so what we would do from here is we would expand this so that we would have this E naught x hat times each one of these terms. But when we look at this, we're going to have an x hat dot x hat and an x hat dot y hat. X hat dot x hat is 1 because these are unit vectors, and x hat and x hat in the same direction. X hat dot y hat is going to be 0 because these two vectors are perpendicular to each other. And so what that says then is that this is going to be equal to the integral of E0 dx, which is just going to be equal to minus E0 times x. So this is what our electric potential function looks like. Okay, so that was the second part. The third part was to draw the electric field, so I already have that here, and then draw several electric potential lines. Okay, so seeing that this electric potential is only dependent on x, if I move up in y, these are always going to have the same values. It's when I move across in x that I have changing values, and so my equipotential lines are going to look like this. So this could be like some v at A, some v at B, some v at C. Okay. Now a rule for the relationship between the electric field and the electric potential that I neglected to mention in the notes is the fact that these are always perpendicular to each other. So for any system where you have some electric field and you want to draw some equipotential lines, or you're given some equipotential lines, you want to know what the electric field looks like, these are always perpendicular to each other. Okay, so now what we want to do is we want to plot this. Well, when we plot this, this is just going to be, if this is v as a function of x, and this is x, this is just going to be some line that goes down like this. So now the question I asked was, if this was a topographic map of a hill, describe what the hill looks like, and the explanation should include a discussion of the equipotential lines as well as the plot of the electric potential function. So if this was a hill, this line in this downward slope is going to represent the hill, so it would look like this. And the equipotential lines are representing points along the hill that all have the same height. So going across like this always has the same height. Okay, the next part was what is the slope of the electric potential function, and how does this relate to the electric field? Well, if we look at this in kind of the classic 7th or 8th grade way that we did things with straight lines, we would say that this is some y is equal to mx plus b, and the m there, the slope, is just going to be this minus E naught. Okay, now when we look at this, this is identically the negative electric field. So the slope of this line is the negative electric field. And then the last thing that we wanted to do once we identified that was to discuss how this answer discuss how the answer to the previous question relates to the equation E is equal to negative grad V. So E vector is equal to negative grad V in general, but in this case, because the electric field is only, the electric potential is only dependent on x, we can reduce this so that this is x hat partial derivative with respect to x of v. And really, when we look at this, we have a negative sign here too. We could say that in the terms of like a pre-calculus class, that this is really the ratio of the change in electric potential to the change in x. So this is minus x hat delta v over delta x. And again, this really gets into this idea that we learned maybe a long time ago talking about slopes, right? Because the slope of a line is going to be the change in the rise over the change in the run. And that's actually identically what this is. Now, the other piece here is this x hat, and the importance of that is it tells you which direction this hill is sloping in. So this one's going to be sloping in this positive x direction, but if the hill was rotated like this, it would be the positive y direction maybe, or like this would be the negative y, and this would be the negative x. So that's the importance of this x hat. It tells you something about the direction that the slope is going to be going. And ultimately why, I started by writing this in its most general form, by writing it in terms of the gradient, which is really the way that you want to think about this, because you can have more general functions. This was probably the simplest example that you could have. But you can have more general functions where the slope is going to be doing things in multiple dimensions. So you want to be able to say which direction is it going to be pointing. And ultimately the questions that we did yesterday are going to be related to that idea. Okay. So any questions about this? Yeah.
Is the word, are you saying equipotential?
Equipotential. Yeah. So somebody could probably remind me of whether this is Greek or Latin, but the root is the same root as equal. So this is the equal lines of equal potential, which is again what this represents here. This line, every point along this line has the same potential. In the same way, when I had this this point charge earlier, and I had my equipotential surfaces that go around it, every point on this surface has the same electric potential. Yeah. Other questions? Okay, so before we start our work, I wanted to go back to one of the problems that we did yesterday in class, and note that there are really two ways that you can go about it, and some people tried to do the more difficult way. But ultimately, if you want to do it like that, you need to be very careful with the way that you're defining the point C along the y-axis. So the problem was you have some charge that's spread from some point y is equal to A to y is equal to B, and there's some point C up here. And you want to find what the electric potential is at C. So find V of C. Okay. So the way that a lot of you went about it, which is not an incorrect way to do it, you just need to be very careful with it, is to first find the electric field and then find V by saying V is equal to the negative integral of E dot dl. So first we would do dE is equal to 1 over 4 pi epsilon naught dq divided by r squared times r hat. And we've done plenty of these, so we can do this really quickly. So dq in this case is going to be the total charge. I'll just say that this is some capital Q divided by the distance. And so this is going to be q divided by b minus a times the infinitesimal length here, which is dl is equal to dy. So this is dy. R is going to be this distance, and this is the distance y. And so if this total distance is the distance c, then r is going to be equal to c minus y. And then the last thing we need is the unit vector that points from here to here, and that's just going to be y hat. So we could put this all together to find our electric field here, and that would be to say that E vector is going to be equal to 1 over 4 pi epsilon naught times the integral from A to B of BQ divided by B minus A dy divided by C minus Y quantity squared y hat. Was there a question? Or I'm just going through this really fast. Yeah. I'm kind of doing that a little bit on purpose because this isn't the important part. I'll come around and answer questions if you have them about this, but really I'm just going through the same process that we always go through. I'm just doing it kind of quickly because I don't want to spend a lot of time on this part of it. Okay, so ultimately this is what you have for your electric field, and what you see here is that when I do this integral, I'm just going to get a number. Right? Because I'm integrating over y, and I have boundaries from a to b. These are all just numbers in the end. So I'm getting a value for the electric field here. And then if I do the integral of E dot dl, this is just the integral of a constant. But when you do this, you need to consider that c could be some arbitrary point. So c has to be some second y, so that when you integrate this dl, it's with respect to that second arbitrary y. And that's how you actually get a function for v, instead of saying that v is just some constant times y. Okay. Now, why I say that is because the second way to do this is, rather than going through the process of calculating dE and then going to v from the integral of E dot dl, what you can do is you can say that dv is equal to 1 over 4 pi epsilon naught dq divided by r. And this in and of itself is a much simpler calculation because I don't even need to know what the unit vector is. And the integral, should I choose to do it, is going to be a little bit easier because it's going to be c minus y, just c minus y and not c minus y squared. And so when I plug everything into this one, this is just going to be 1 over 4 pi epsilon naught. This is q divided by b minus a times the integral from a to b of dy divided by c minus y. Okay, and this was ultimately what you should have. And again, in order, you see that this one, when I integrate this, I'm going to get some natural log, right? If you're used to doing these kinds of integrals, I can put a negative sign here, I can put a negative sign here, then the derivative of the bottom is identically on the top. I get some natural log, which is different than what I would get if I did this integral and then I plugged it in here, treating c as a constant. So the punchline here is, always try to do it this way. If I ask you to find some electric potential from some distribution of charge, just go straight to finding what dV is. Don't go through this process of finding dE and then finding E, because even if you wanted to do this, which is more difficult, you have to be very careful with the way that you do it. You can't treat C as a constant. You need to treat C as a variable, which conceptually is kind of difficult to understand, but it works out properly if you do that. Okay. Any questions about this aside from the fact that I talked too quickly? I can go over it some more. Yeah.
All right. So if you're treating C as a variable, don't you have to integrate with respect to C?
Yes. Ultimately, that's what this would be. Okay. Yeah. And there's slightly different notations for this. What I would probably do is I would call C y. I would call y prime. But again, this is why I'm not doing this with you guys. Just go straight to this. But you can, if you want to check in your own free time, do this integral with c as a variable and then integrate with respect to c. You'll get the same thing.
Okay.
Okay.
So when we do that, do we treat y as constant, or do we are we?
You're integrating out y here, right? So when you do this integral, you don't have any y's anymore. And then you only have a, b, and c. A and b are constants. But if you treat c as a variable and then integrate over that, then you're removing the c from the equation. Or, well, let me think. So when I do this one, yeah, this is complicated because then this y and this y are actually kind of the same. I'm playing around with my labels a lot here, but again, that's why it's kind of complicated. Ultimately, this v is a function of c. When you do this, you want to do it as an indefinite integral, so you still have the c dependence in it. And then you would get that to be some function of c. But again, a way that you can think about this, instead of saying dl is y hat dy, call it y hat dc.